Hello everyone and welcome back to Tutorial 6 of MIE100, the Dynamics course in the University of Toronto. Today we're continuing our tutorials on kinetics of particles. This time we're going to go a little bit into impulse and momentum. We're going to be doing 3 problems in total, and we're going to see a little bit of conservation of momentum, so stick around, and if you have any questions, please leave a comment in the comment section below. Okay, so starting with the first question, we've got a slider of mass m1 is 0.4 kilograms, moving along the smooth support surface with velocity v1 is 5 meters per second, when in the position shown. After negotiating the curved portion, it moves onto the inclined surface of an initially stationary block of mass m2, 2 kilograms. The coefficient of the kinetic friction between the slider and the block is 0.3. Determine the velocity of the system after the slider has come to rest relative to the block. Okay, so the velocity after the slider has come to rest relative to the block. Neglect friction at the small wheels and neglect any effect associated with the transition. Okay, so first we want to find the speed of the slider, v2. So this is what we want to find. This is v1 over here. And we want to find v2 as the slider moves onto the block over here. So we're going to start with the kinematics equations. Which is v2 squared is equal to v1 squared plus 2as, which is equal to v1 squared minus 2gh. So if you plug in here the values that we know, we get v2 is equal to 3.9 meters per second. Now we're going to talk a little bit about some new material here. We've got impulse and momentum. So the sum of forces is equal to g, which is the linear momentum. G is equal to mv. And to find the linear momentum, we need to do the conservation of linear momentum. So the conservation of linear momentum equation is equal to delta G is equal to 0, or G1 is equal to G2. So the momentum in both systems, so the momentum always has to be equal. So going back to our problem over here, conservation of system linear momentum in the x direction this way is going to be m1 v2 cosine 20, because that's basically the angle at the ramp, and we're going to make that equal to m1 plus m2 v. This is the whole system. all right? And since we have all of our values, we can find our velocity to be equal to 0.61 meters per second. And it turns out that the value of the coefficient of friction is irrelevant. Okay, now for the second question, we have a hollow crate of mass 50 kilograms mounted on frictionless wheels that ride on the ground. Inside the crate is a box of mass 20 kilograms mounted on frictionless wheels. At time t is 0, the system is released from rest with a spring having an initial length of 0.4 meters. The spring constant is 30 newtons per meter, and the spring has a relaxed length of 2.5 meters. What is the initial potential energy of the spring, the initial acceleration of the box, and the speed of the crate when the spring reaches a length of 1.5 meters? Okay, so for the first question, we want to find the potential energy of the spring. So we're going to recall the elastic potential energy equation. Which is VE is equal to half kx squared, or half k L naught minus L1 squared, where L naught is the relaxed length and L1 is the initial length. So VE1 is going to be equal to half 32.5 minus 0.4 squared, which will give us 66.15 joules. Now for part B, we want to find the acceleration of the box at the initial state. So let's draw here a little free body diagram. We've got the big crate and the box inside. So this is MB, and this is MC, the mass of the crate and the mass of the box. We've got the spring pushing with a force Fs. And now we're going to use Newton's second law. We've got the sum of forces in the x direction is equal to MAX. We know that the force that the spring applies onto the box is mb, the mass of the box, multiplied by the acceleration of the box. And the force is going to be equal to, so force of the spring is just the stiffness of the spring, K L naught minus L1. So we plug in here the values that we have. And the value for our acceleration is 3.15 meters per second squared. Now for part C, we want to find the velocity, the speed of the crate at L2 is 1.5 meters. So let's draw a free body diagram for that. At this point, we've got the box inside of the crate, and the spring has been released, so it's moving the box this way. So this is the velocity of the box. Now, due to that force of the spring moving the box this way, the crate will be moving in the opposite direction. Okay? Now, to find this velocity over here, we need to do some energy conservation equations. So we know that delta T plus delta V, the kinetic plus the potential energy, is both equal to 0. And that means that T2 minus T1 plus V2 minus V1 is equal to 0. Now T1 is 0 because V1 is 0. Initially, it's at rest, so there's no velocity. So T2 is going to be equal to half mb vb squared plus half mc vc squared. And we've got the potential elastic energy is going to be equal to half k L naught minus L2 squared minus MIE1, which we found in part A. Now it's all about plugging in our values. Which simplifies to this equation. 10 VB squared plus 25 VC squared is equal to 51.15. Now, because we have one equation and two unknowns, we need to come up with another equation. So we're going to use the conservation of linear momentum that we just learned in the previous question. So conservation of linear momentum, which is G1 is equal to G2. And G1 is the sum of mass multiplied sum of velocity and V. And same here. However, this is going to go to 0 because V1 is 0. So here we've got MB VB minus MC VC because they're in opposite directions. And once we plug in our values, we now have two equations and two unknowns. Two unknowns. Therefore, we can do simultaneous equations. To give us VC2 is equal to 0.76 meters per second. Now for our last problem, we've got a particle of mass m that moves on the inside surface of a smooth conical shell and is given an initial velocity v0 tangent to the horizontal rim of the surface at A. So as the particle slides past point B, a distance z below A, its velocity v makes an angle theta with the horizontal tangent to the surface through B. So determine the angle theta and the speed v. So we don't have any numbers in this question. There's a lot of variables and a complicated shape. So let's start with some background. This is going to be new material. Now we know the linear momentum conservation equation, but we don't have a linear momentum here. We have an angular momentum. So as we know, angular tends to be a little bit more difficult than the linear one. We have angular impulse and momentum equations, which is basically equal to h naught is equal to r times mv, where r is the radius, m is the mass, and v is the velocity. Now, the conservation of angular momentum is very similar to the linear one. It's just delta h naught is equal to 0, or h1 is equal to h2. So going back to our case over here, we have A and B. So the momentum at A is going to be equal to the momentum at B. Now here we have a complicated shape, and we want to find the value for R. Okay, R here is basically, the distance from the y-axis to B. We know that the distance from A to the y-axis is R naught, and we know that B is Z, is a distance Z away from A, but we don't have this distance over here. So we're going to try to find that using simple geometry. This is R naught, and this is H. This is A over here. This is the y-axis. And we've got B somewhere over here, right? We know that this distance over here is Z, and we want to find R. So, because those are similar triangles, we can do R naught over H is equal to R over H minus Z. Once we rearrange that, we get R is equal to R naught minus R naught Z over H. It's just a geometry trick. Now that we've got both, we can now plug in our angular momentum equations. So it's going to be mv naught R naught is going to be equal to mv R, which is R naught minus R naught Z, H cosine theta, because it's at an angle. Now we're going to do our energy conservation equations, which is TA plus VA is equal to TB plus VB. You know that the potential energy is going to be 0 at A, because H is going to be equal to 0, HA. It's at the top of the rim, so there's no height. TA is going to be equal to half mv naught squared, which is equal to TB, which is half mv squared, and VB is minus mgz, because it's a z distance below A. Now this is going to simplify to V is equal to E naught squared plus 2 GZ under the square root. That's the value for v. Now, if we plug that in to our equation here, we get mv naught r naught is equal to m multiplied by v, which is now v naught squared plus 2gz all under the square root, multiplied by r naught z h cosine theta. And once we simplify all of that, we get theta is equal to cosine v naught over v naught squared 2gz under the square root 1 minus z over h. And that's our final answer for theta. That was the end of our tutorial. Thank you so much for sticking around. If you have any questions, email me on noor.doedar@mail.tutoronto.ca or leave your questions in the comment below. See you next week.